All right, let's look at section 1.4, cosets and counting. The abstraction starts to pick up a little bit in this section. What we're going to do, kind of a big picture idea, is generalize the idea of congruence mod n on the integers to a more general setting, to the setting of arbitrary groups. The same approach is taken in the undergraduate class, but we'll deal with it in a little more hands-on way with an equivalence relationship. In the undergraduate class, you usually approach this by starting with a homomorphism between groups and looking at the kernel of a homomorphism to get a normal subgroup. We'll end up all in the same spot. But we're going to deal with a congruence relation modulo a subgroup. And so we'll start there. Definition 1.4.1 says, let H be a subgroup of G, A and B, elements of G, A and B, or A is right congruent to B, modulo H, denoted A congruent, little subscript of an R, A is right congruent to B, modulo H, if AB inverse is in H, A is left congruent to B, modulo H, denoted A, lowercase l, congruent, A is left congruent to B, modulo H, if A inverse B is in H. So there's the two relationships related to left and right congruence, mod, a subgroup, H of a given group, G. And we're going to define cosets, and we'll define cosets ultimately in terms of these congruences. So we'll use left and right congruence to define, respectively, left and right cosets. We'll use this coset idea to prove Lagrange's theorem and consider things related to the orders of subgroups using Lagrange's theorem. And ultimately, under appropriate conditions, we'll even make a group out of the cosets. Possibly we saw some of this stuff earlier. I think the first section had some exercises related to this. But we'll deal with the groups of cosets in the next section. Okay, to get things started, some properties of these congruence relations. The setting being, in Theorem 1.4.2, let H be a subgroup of a group G. First, right and left congruence modulo H are, in fact, equivalence relations on G. So we'll need to show reflexive, symmetric, and transitive. Follows straight from the definition. The equivalence class of any A in G under right congruence, modulo H, is the following set. We'll denote it as H times A. So we're taking a subgroup and multiplying every element of that group on the right by element A. And by the way, all these group products make sense because we have the big umbrella group G and everything's happening inside group G. And so the symbol capital HA represents the product of all elements, lowercase h, of subgroup H when multiplied on the right by A. If we wanted the left congruence class, then we denote that as A capital H, move the A to the other side, and we take all products of the form A lowercase h, where lowercase h ranges over the subgroup capital H. So the claim is these are the two congruence classes, and the final claim in this theorem is the cardinality of HA is the same as a cardinality of subgroup H is the same as the cardinality of A capital H, this holding for all elements A of G. And to get the word out, so definition snuck in here as well, subgroup H times element A on the right is called a right coset of H in G. A times subgroup H is called a left coset of H in G. So there's formally the definition of cosets. And maybe to reiterate, we can say the right cosets are equivalence classes under congruence modulo H is given here. Part 3 tells us about the cardinality of cosets in the subgroup. We're going to deal a bit with this cardinality stuff. No problems saying these three cardinalities are the same. Two sets are the same cardinality if there's a bijection between the two. I don't want to say they got the same number of elements because that has a finiteness implication. They have the same cardinal number, but that's a bit of a deeper set theoretic story. So we'll establish really all of our cardinality claims using bijections. If we have finite cardinalities, then we can talk about numbers of things, and we can maybe even talk about division. Right? Division makes sense for natural numbers. So it makes sense for cardinalities of finite sets, but division doesn't make sense for cardinalities of infinite sets. We can multiply cardinal numbers, more on that shortly, but it doesn't make sense to divide one cardinal number by another. So let's look at a proof of theorem 1.4.2. Okay. So we got 3 claims. None of them terribly complicated. First claim, right and left congruence modulo H are in fact equivalence relations. Okay, let's denote right congruence simply as congruence. We'll go through the argument for right congruence. The argument for left congruence is very similar. So let A, B, and C be elements of group G. The claim is A is congruent to A. That is, we have reflexivity because being congruent means A congruent to B, A right congruent to B, means AB inverse is in H. Well, a claim that A is right congruent to A would be a claim that AA inverse is an element of H. Of course it is, because AA inverse is the identity. H is a subgroup. It's got to contain the identity. So there's the property of reflexive. Symmetric, if A is right congruent to B, then AB inverse is in H, very definition of right congruent. Since H is a group, then the inverse of this element of H is again in H. That is, AB inverse is in H. AB inverse is, usual way of taking the inverse of a product is B inverse to B times A inverse. So we draw the conclusion that BA inverse is in H, simply group properties applied to H. Well, that means B is right congruent to A. So if A is congruent to B, right congruent, then B is congruent to A, right congruent. That is, we have symmetry, so reflexive, symmetric. Transitivity is the cutest one, I suppose. If A is right congruent to B and B is right congruent to C, then we have AB inverse is in H from the first one. BC inverse is in H from the second congruence assumption. Let's take these two elements of H and multiply them together. Take AB inverse times BC inverse. Associate the B inverse and the B. Let's not dwell on that too long. We're developing a bit of knowledge on this stuff. I can cancel the B's. We get AC inverse as an element of H. That is, A is congruent to C. A is right congruent to C. And so we've got A congruent to B, B congruent to C, implies A is congruent to C. We've got transitivity for right congruence, and left congruence is quite similar. So that establishes part one. We do have an equivalence relation. By the way, equivalence relations partition up a set, the set on which the equivalence relation is defined. So that we're going to get a bit of mileage out of that, knowing we have an equivalence relation. Secondly, claim is the equivalence classes, which, by the way, will partition up whatever the equivalence relation is defined on. The equivalence class of A and G under, say, right congruence modulo H is the set H times A. And we talked about this earlier. The equivalence class of A under left congruence modulo H is this left coset. So right congruence, right cosets. Left congruence, left cosets. Okay, so we need to establish that. We'll just write out what we mean by the congruence. So suppose we take all X and G such that X is, again, we'll have a discussion about right congruence. X is right congruent to A. So that'd be the X and G such that X A inverse is an element of H. That's what the definition of right congruence is, modulo H. That'd be all X and G such that XA inverse, element of H, let's call it lowercase h. XA inverse equals lowercase h for some lowercase h in subgroup capital H. So just an introduction of a new notational thing. I want to do that. So now I can look at this little equality, XA inverse equals H, and rewrite it as X equals HA. Multiply both sides of this little equation on the right by A and simplify. So we get X equals HA as H ranges over subgroup H. We're taking all X and G of that form. That's exactly what we claimed. We're getting all HA such that H ranges over subgroup capital H, and that symbolically is what we've called the right coset capital H times A. So everything which is right congruent to A modulo H is in this coset, and similarly for left congruence. The last claim is a cardinality claim. Right coset, left coset, and subgroup H, all three of those things are of the same cardinality. To establish equality of cardinalities, we need bijections. So define alpha that maps the right coset into H, define it as alpha of element HA. That's what elements of that right coset look like. Right coset has these things as their elements, right? So alpha of this element of the right coset is mapped to just H itself. Simply drop the A. We're going to claim that's a bijection. First, if alpha H1 of A equals alpha H2 of A, so we've chosen two different elements of this right coset. There's what the elements of the right coset look like. A comes to us as fixed, started with a given A in the group. It's the H that can vary. As the H varies, we get different elements of subgroup H times element A. So we get, say, an H1A and an H2A, for example. Well, that means, by the very definition here, that alpha of H1 of A is simply H1. Alpha of H2 of A is simply H2. So if we put these things in, H1A and H2A, then we have the equality H1, H2. That's the very definition of one-to-oneness. So we've got a one-to-one, if you like, an injective mapping. I'm not worried about structure here. I'm not worried about any homomorphism stuff. We're talking about sets. So it's simply a bijection argument. There's the one-to-oneness. Now we just need the onto-ness. Take an arbitrary element of subgroup capital H. What you're going to map to what element of the coset, what element of HA, will you map to that subgroup to get out this lowercase h? Well, of course, you map element H times A with alpha to get the H out. H is an arbitrary element of subgroup capital H. There's what it's the image of. Alpha of this thing equals that. So we've got an onto mapping. We have a surjection, if you like. We got one-to-one. We got onto. We got injective and we got injective and surjective. We got a bijection. So the cardinality of the right coset is the same as the cardinality of H. And I don't think it takes a whole bunch of creativity to guess how you'd do this for the left coset. We'd map A times H to H and repeat this argument. So we get that claim on the cardinalities of the cosets. Maybe make a little bit of a big deal out of this. We're good, even if these subgroups in these cosets are infinite, because we used a bijection. That works in the finite or the infinite case. If I want to count stuff, I'm stuck doing finite things. And this is graduate algebra. We'll deal with infinite groups, infinite sets. So we're good because we used a bijection. Whenever we make a cardinality claim, we're really making a claim about a bijection, even in the finite setting. But we have to use a bijection argument if we have infinite things. A corollary to that result, talks more about some relationships between cosets, and I want to go through proof of a piece of this. It talks about how many left and right cosets there are. So we'll have two cardinalities that will deal with how big the cosets are and how many of them there are. The setting is H is a subgroup of group G. The claim is G is the union of the right cosets of H and G. Oh, and G is the union of the left cosets of H and G. Kind of keep those segregated. So two statements there. Two right cosets of H and G are either disjoint or equal, and the same goes for the left cosets. For A and B and G, we have the right coset HA equals the right coset HB if and only if AB inverse is an element of H. And by the way, we could reword that as A is right congruent to B modulo H, because that was a definition of right congruent. If we look at left cosets, the left coset AH equals the left coset BH if and only if A inverse B is an element of H. And of course, that was the very definition of left congruent. A is left congruent to B. So can actually, so we'll make an observation when we get done reading the definitions of the statement. If calligraphy R is the set of distinct right cosets of H and G, calligraphy L is a set of distinct left cosets of H and G, then those things are equal. That is, the cardinality of the collection, cardinality of the set of right cosets is the same as the cardinality of the set of left cosets. I so desperately want to say there's the same number of right cosets as there are left cosets. Yeah, that's the idea, and that's perfectly fine if there's a finite number of them, but saying number of is kind of indicative that there's a finite number. Unless I say the cardinal number of, then I'm good. But the cardinality of the collection of right cosets is the same as the cardinality of the set of left cosets. Some commentary. Parts 1 and 2 say G is the union of the right cosets of H, and the right cosets of H are either disjoint or equal. That's what a partitioning is. So part 1 and 2 here combine to tell us group G can be partitioned into the right cosets of H and G, or the left cosets of H and G. A partition is taking a thing, a set, and breaking it into a bunch of pieces, where everything in the original set is in one of the pieces, and the pieces are disjoint. So everything's there, and the pieces are disjoint. That's what the very definition of a partition, and that's exactly what we're getting here. Everything is there, and the pieces are disjoint. We made an observation about part 3 can be re-expressed in terms of congruence. And this last claim, part 4, is a cardinality claim. Well, if it's a cardinality claim, we need ourselves a bijection. So let's establish that using a bijection argument. And I just want to prove part 4 of this one. Define alpha mapping the set of right cosets to the set of left cosets as follows. Define alpha of coset, right coset, HA. Define that to be left coset, A inverse H. Remember, I ain't worried about structure. We're not doing homomorphism stuff here. We're just counting. I'm just worried about cardinalities. Worried about one-to-one and onto, injective and surjective. I want this to be a bijection, and it only takes a little bit of an argument to show that it is. Of course, we'll use some of this other information here. If alpha of HA equals alpha of HB, so we've put these two right cosets into alpha. We want to draw the conclusion that the two cosets are actually the same. So we get the same output only when we put in the same input. So if alpha of this right coset HA equals alpha of this right coset HB, then A inverse H equals B inverse H, because that's what the mapping is. Takes the right coset HA to the left coset A inverse H. So very definition of our mapping. Okay, here we got equality of two left cosets. We said in part 3 that we get equality of two left cosets, AH equals BH, if and only if A inverse B is an element of H. So we need to translate this into that lingo. So we'll take an inverse of this, multiply it by that, and say that has to be an H. A inverse inverse, B inverse is an H. That's exactly what part 3 says. Translated from A and B up here to A inverse and B inverse down here. Of course, we pick up an inverse inverse on one of them. A inverse inverse, B inverse, that's the same as A, B inverse. So A, B inverse is an H. Part 3 deals with that as well in terms of right cosets. Hey, if AB inverse is an H, if AB inverse is an H, then if and only if the right cosets HA and HB must be the same. So we draw the conclusion, right coset HA equals right coset HB. And again, what we've shown is if I get the same thing out of this mapping alpha, then I must have put the same thing in. And the thing that goes in is a right coset. We've got one-to-oneness. Onto-ness, we're mapping right cosets to left cosets. Pick an arbitrary left coset. We need to show that under alpha, it's the image of some right coset. Consider the right coset, H, A inverse. Under the mapping, this is mapped to A inverse inverse H. Given mapping we have here, replace the A with an A inverse, produces this. A inverse inverse is A itself. So this arbitrary left coset under alpha is the image of something. In fact, it's this something here. It's this right coset here. So alpha is onto, alpha is surjective. So alpha is a bijection, and the cardinalities of these two sets are the same. The cardinality of the collection of right cosets is the same as the cardinality of the collection of left cosets. So we've established, if you will, informally, how big the cosets are, and in some sense, how many of them there are. Cardinalities we've established. A quick little comment about notation. So far, it's only been only been multiplicative notation. Were we to do this in additive notation, if we had an additive group, we'd say A is right congruent to B means A minus B is an element of H. For cosets, we would take a right coset of H to be H plus A, all lowercase h plus A instead of the multiplicative notation. As usual, we'll have discussions almost entirely in terms of multiplicative notation, and we'll probably have a handful of examples that are additive examples, so it's worth making that comment. New definition. This also counts something. Well, counts a bit of a misnomer. Describes a cardinality of a set. Definition 1.4.4. Let H be a subgroup of a group G. The index of H and G, denoted with these square brackets in the colon, and red, the index of H and G, sort of read a little bit backwards, is the cardinal number of the set of distinct right cosets of H and G, or left cosets. We just saw that that's the same. The cardinal number of the right cosets is the same as the cardinal number of the left cosets. So this represents the cardinality of the collection of right cosets or left cosets of H and G. Really want to say number, and for pedagogical reasons, maybe just be careful with that. Cardinal number is the right thing to use. It's like we're counting something. Yeah, you don't want to imply that it's finite or countable even necessarily. So that's a poor choice of words, but I am looking for some informal understanding here. So index involves the cardinal number of the cosets of H in G. If G and H may be infinite, speaking of cardinalities, yet the index could be finite. Consider the integers, and let's take the subgroup generated by M, where M is anything other than 0, so don't use a trivial subgroup. Remember, all subgroups of the integers were of the form group generated by M, where M was the smallest positive integer in that subgroup. For example, if it's 2, then we got the even integers. If it's 3, we've got all integers, 0 mod 3, multiples with 3. And if we count the number of cosets, say the even integers, subgroup generated by 2, there's only 2 of them, the even integers and the coset of the odd integers. Of course, the odd integers are not a subgroup, right? Maybe it's worth commenting. These cosets, they're cosets. They're not necessarily subgroups. In fact, they're not subgroups. H is a subgroup, and these other things are sets. I don't know what the co and coset is inspired by, but the cosets are not subgroups, except for H itself. H itself counts as a coset, but that's the only one in that collection of left to right cosets of H that's actually a subgroup of group G. The others are just sets of elements. So were we to take M equals 2, and we counted the number of cosets of the even integers in the integers, there's 2 of them, the even integers themselves and the even integers plus 1, that is the odd integers. And sure enough, the even integers and the odd integers, they partition up the integers. The even integers are that subgroup. The odd integers, not a group. Doesn't have 0 in it, so it doesn't have the identity. Talking additive groups here. The extreme values, as it were, of the index occur when H is the identity only, when H is a trivial group, and when H is the whole group itself. Right? These are sort of the endpoints of the, and as big as G itself. Nobody said anything about proper non-trivial in this setting. If H is simply the identity element, then G mod H, or excuse me, get ahead of myself with the verbiage, the index of H in G, I should say, is the cardinality of G. If H equals G itself, then the index of G in G is simply 1. There's only one coset. It's the whole group itself. So these are the extremes in terms of cardinalities of that index value. The following is quite useful because we'll use it to prove Lagrange's theorem. Lagrange's theorem should ring a bell from your introduction to algebra experience. Theorem 1.4.5 says, let K, H, and G be groups, where K is a subgroup of H is a subgroup of G. The claim is the index of K in G equals the index of H in G times the index of K in H. We're doing index of K in G, the outer ones, in terms of the index of H in G and the index of K in H, and we're multiplying. Comment there about multiplying cardinal numbers. Makes sense to multiply cardinal numbers. You do so by taking cardinalities of Cartesian products. The cardinality of set A times the cardinality of set B is the cardinality of the Cartesian products of set A and B. A Cartesian product B, the collection of all ordered pairs. Some of this is probably in chapter 0. This is set theory background. And when we go through the proof of this, we're going to see some ordered pairs of indices, and the sizes of those indexing sets, the cardinality of those indexing sets will reflect the cardinality of these indexes. If any 2 of these indices are finite, and so is a third. Yeah, if I've got this equals that times the other thing, if any 2 of those are finite, then certainly the third one is. There's little really to prove, more of an observation there. Oh, if we're dealing with finite things, then I could do some division, and I could divide maybe both sides by, I don't know, the index of G and H or something like that. We could actually do division if these things are finite. That's the thing with cardinal numbers. With cardinalities of sets when they're not finite. You can multiply them You do it using Cartesian products, but you can't divide infinite cardinal numbers. I can only do division stuff when we're talking about finite things. And this will pop up. There's some comment about division at the bottom of the slide. This will pop up in Lagrange's theorem, but only in the connection when we have something as finite. Division only makes sense when you have finite sets. If you have infinite sets, I can multiply their cardinalities together. Let's do it in Theorem 1.4.5. Okay, so here's the claim, a little bit cleaner here. Don't have a new line in the middle of that statement. All right. We're going to take G and write it as a disjoint union of right cosets. Remember that corollary, parts 1 and 2 said the right cosets of H in G partition G. So we're doing a little thing here first, using a union symbol with a dot in the middle of it to indicate that this is a disjoint union. In algebra, the disjointness is not necessarily an issue often. It is here because we're trying to, I want to use the word count, we're trying to establish a cardinality result. But we do get this disjointness. Corollary 4.3 told us right cosets partition G. But what we're doing here is picking an A sub I in G for each right coset. So when I equals one value, and I don't want to say the first, that implies countability, I choose some value in this indexing set capital I, then there is an element of G such that we get coset H A sub I. There's probably a whole bunch of elements of G that'll produce that same coset. Pick one, call it A sub I. So what we're doing is choosing these A sub i's, as I ranges over indexing set capital I, to consist of exactly one element from each right coset of H in G. So in that way, we get each right coset exactly once. So that's how we can use the partitioning idea and tie it to, in a sense, specific elements of group G, the A sub i's. This set of elements of G is called a complete set of right coset representatives. All right, so we're getting all of the right cosets by choosing a single representative from each coset. If you're big time into set theory, and there might be some axiom of choice stuff going on underneath this. All right, how many representatives did you choose? Well, one for every coset of H and G. What's the cardinal number of the cosets of H and G? That's what these symbols, that index thing, that's what it denotes. So the number of A sub i's, the cardinal number of the A sub i's equals the value of the index. Excuse me briefly on some rigor. The number of A sub i's you got over here is the same as the number of cosets you got over here. Okay, I shouldn't say number because of the cardinal stuff. But informally, that's kind of the idea behind it. Formally, it's cardinal numbers. How many A sub i's do you have? Well, what's the cardinality of that collection? Well, you got one for every element of this indexing set, capital I. I can also say, kind of for free, it's the cardinality of that indexing set, capital I, for what it's worth. So this allows us to write G as a disjoint union of right cosets of H. But K was a subgroup of H, so we could do the same thing for the right cosets of K in H. Similarly, that is, we could take group H and write it as a disjoint union of right cosets of K. Let the indexing set be J, and as these indexing sets are going to play a big role, it's how we're going to quote unquote count things. So the indexing set is capital J. These B sub j's, as J runs over, index J runs over set capital J, is a complete set of right coset representatives of K and H. So same idea as what we just did. Again, we'll get the cardinality of the indexing set J equals the index of K in H. One more time informally, there's the same number of indices as there are cosets of K in H. There's the same cardinal number of indices as there is the cardinal number of right cosets of K and H. Okay, so same idea recycled. We know the right cosets, as we've chosen them, are mutually disjoint. We know the right cosets of K are also mutually disjoint. Same reason, Corollary 4.3, part 2 told us about the disjointness of those things. So we can write G, as we did, as a disjoint union of the H sub i's, as we did in the first line of the proof. We know this H itself can be written as a disjoint union of right cosets of B. So we get a disjoint union there as well. So all I did was replace the capital H with this little disjoint union here to produce this. All right. That gives us a union over all I in set capital I and all J in set capital J of K, B sub J, A sub I. So the meaning of this multiplication of these sets is simply this thing here. Now the question is, not a typo here, do you still have the disjointness when you deal with a collection in this form? That's what we need to show. I want to show we still have the disjointness. And then we'll go through and relate what we're getting here to this index. What we've got here is, you'd agree, these are all right cosets of K. There's K. It's multiplied on the right by something or other. So these are right cosets of K. You know G equals this. Is it a partitioning? Becomes a question. It is. These turn out to be mutually disjoint. If you will, how many of these do you have? How many of these right cosets of K and G do you have? How many? What's the cardinal number? What's the index? What is the index of K and G? Here we've got right cosets of K in G. We need to count them, as it were. We need to discuss the cardinality of them. We'll do that by finding the cardinality of the Cartesian product of index set I with index set J. All right, so first, suppose these right cosets in this collection, suppose they're not mutually disjoint. We'll get a contradiction to that, and then we'll see how many of these there are by seeing how many indices there are, by finding the cardinality of this Cartesian product. All right, these right cosets of K, they're still cosets of K in G because they're multiplied on the right by an element of G. Yeah, everything is an element of G. We've got the big umbrella group, G, and this other stuff happens inside group G. So we're okay on that. We were dealing with a bunch of right cosets of K. So if they're not disjoint, then they got to be equal. Remember, right cosets were either equal or disjoint, Corollary 4.3, part 2. So we've assumed not disjoint, so we must have some right coset equal to some left coset where at least one of these corresponding indices are different. That is, K, B sub J, A sub I must equal K, B sub R, A sub T, where either the indices on the B's are different, the J's and the R's, or the indices on the A's are different, the I's and the T's. Okay. But then we've got equality of these sets. One of the elements over here, say we just choose an element of subgroup K to produce one of these elements. Let's choose the identity over here. Choose the identity from subgroup K that produces B sub J A sub I. Well, on the right-hand side, since two sets are equal, there's got to be an element of this set that equals this B sub J A sub I. Call it K times B sub R A sub T. If the sets are equal, certainly I can choose the identity on this side. There's a choice for an element of K on the right-hand side that produces the same thing. The sets are equal, they contain the same elements. So we're led to consider this kind of equation here. Now, H was a subgroup of G, K a subgroup of H. H is the middle group. What we're doing here is the B sub J and B sub R, those were chosen in H because we got to this stage by taking right cosets of K in H. That's where the B's came from. The K we've chosen here is in subgroup K. It's also in subgroup H because subgroup K is a subgroup of H and G. But we can draw this conclusion. So we've got the B's and the K, we got them all in the same spot. We got them in subgroup H. So right coset H times A sub I is the same as right coset H B sub J times A sub I. What is that? Remember, B sub J is in subgroup H. So if I take B sub J and multiply it by all the elements of subgroup H, I simply get subgroup H back. It permutes the elements in some fashion. So by taking an element of H itself, multiplying on the right, I just get the subgroup H again. In the finite setting, think about it as if I look at the multiplication table, the Cayley table of a group, if I read along one of the rows, then all the elements of that group are there. It's kind of that idea is what's happening here, though I'm not implying finiteness or countability or anything like that. So that's the reason that justifies this set equality. We're saying these two sets are equal. We could bracket off using associativity element-wise and the meaning of these symbols. And now we've got a B sub J A sub I here. Well, B sub J A sub I, we've deduced under our hypotheses, equals K B sub R A sub T for some K. So we're making a substitution there. For the B sub J A sub I, we're substituting that quantity, K B sub R A sub T. All right, let's drop the parentheses. And just like I was able to introduce a product on the right by an element of H here, I can absorb elements of H into that set. We've got H times K on the right, but K is an element of H. So that K can be absorbed in H and you get the same set. Hey, B sub R was in H as well. It can be absorbed too. I actually absorb the K and the B sub R into the H. What we'll get by taking all those products is simply H again. And so we've got H A sub T. So we've got the conclusion from this that H A sub I equals H A sub T. We have these cosets equal. Next claim is that implies I equals T. Just because the right cosets are equal doesn't mean these things we multiplied on the right are the same. Yeah, but we chose those subscripted A's to be a set of representatives of the right cosets. So there was only one subscripted A from each coset. These cosets are the same. This coset contains A sub I. Take the identity in H, produces an A sub I. This one contains A sub T. Well, they got to be the same then. So for that reason, because of the way we chose the A sub I's, a unique A sub I from each right coset, we draw the conclusion I equals T. Okay, so now we've got the conclusion I equals T, leading us to replacing in this previous equation, B sub j a sub I equals k b sub r a sub t. This little thing we had up here, saying, hey, both of these are the same. We can use cancellation on the right to get rid of that and get b sub j equals k b sub r. So if we look at the right coset k b sub j, we can, remember the little k came from subgroup K. We can insert a K there, as discussed earlier. It's the same set of elements. We got the, excuse me, what have we done? We substituted here. Excuse me. Substitute for the B sub J, K B sub R. Substitute K B sub R. And let me recycle that argument, but backwards. Ooh, the K here, lowercase k, is in that subgroup, so we can absorb that K. Lowercase k into the k, think of it as a row of the Cayley table. And we get kb sub r. Now we've got these two right cosets equal to each other. In general, that doesn't mean the b sub j and the b sub r are equal, but it does here because we chose the subscripted b's as a set of representatives of the right cosets of k in H. Same reason we draw the conclusion about I equals T. So we got I equals T and J equals R. So we've shown that we get equality here if and only if, well, only if I equals T and J equals R. That's a contradiction. We assumed at least one of these were different, right, in the disjointness. So we really do have a disjoint collection. All right, I got about 4 lines left to go in this one. Let's go back. All right, what we've done, I can put a dot there now because we know those are disjoint now. So we've got G written as a disjoint union of this batch of right cosets of K. We've then partitioned up G into this collection of right cosets of K. So we've got a complete collection of right cosets of K in G. So, forgive me again briefly, the number of these right cosets is the index of K in G. Okay, the cardinality over here is this cardinality, the index of K in G. So the question is, again, informally, how many right cosets do you have? One for every ordered pair of indices. That is, we need to address the question, what's the cardinality of the Cartesian product, IJ? Remember we had the cardinality of indexing set I was the index of H and G, and the cardinality of indexing set K was the index of K in H. We're about to use that. Okay, back to where we were. The cosets, these right cosets, are mutually disjoint, and the number, the cardinality, the cardinal number of such cosets is cardinality of the number of pairs, that is the cardinality of the Cartesian product of those two indexing sets, and what you mean by the cardinality of a Cartesian product is the product of the cardinal numbers. That's actually the definition of a product of cardinal numbers. If everything's finite, it's obvious, but it's not necessarily finite. And it's the definition of product of cardinal numbers that allows us to do this. So the cardinality of the Cartesian product, that is the number of ordered pairs, i's and j's, that act as indices on these things, is this cardinal number times that cardinal number. But we had cardinal number I as the cardinality of the number, the index of H and G, and for J, we had the index of K and H. So we'll substitute those in, and there you go. The cardinal number of the right cosets of K and G equals a cardinal number of right cosets of H and G times the cardinal number of the right cosets of K and H. All right. we had to deal with this Cartesian product. We can't count stuff because these things are infinite. The last little line says the last statement of the theorem is obvious. The thing about if two of these are finite, then so is the other. In fact, you probably have some experience with this in a finite setting, and you probably didn't have to go through all of this stuff. What caused the difficulty in this is this, I got to get to this cardinality of the Cartesian product to introduce the product of the cardinal numbers in the infinite setting. Okay, we're good to go to state Lagrange's theorem and to prove it with that previous result established. The Lagrange's theorem is an easy corollary of that last result. It says if H is a subgroup of group G, then the cardinality of G is the index of H in G times the cardinality of H. In particular, if G is finite, I can say the number of elements in group G is the number of cosets of H in G times a cardinality, times a number of elements in H. If G is finite, I can say number of without any apologies and without worrying about the cardinal number stuff. Well, that makes perfect sense. We've said I take G and we partitioned it into these cosets. This tells you how many cosets you have, and this tells you how big they are. Multiply those two together, gives you the total collection of the elements of group G. So when I have it interpreted in the finite case, it's not surprising. It's just a little bit trickier when we deal with it in terms of the infinite case. We in graduate algebra now, so the infinite stuff is on the table. But what they say here is if G is finite, then the order of any element of G divides the order of group G. The order of any subgroup of G divides the order of group G. And that might sound familiar to you as Lagrange's theorem from senior level algebra. But I can't use this word divides unless we have finiteness. I can multiply cardinal numbers by considering the cardinality of the Cartesian product, but division of cardinal numbers, infinite cardinal numbers, is meaningless. Multiplication, okay, division not. So, by the way, that's the reason in the finite case, they talk about division. And in the finite case, this all makes pretty good sense. We'll go through the proof. It's quite brief with what we know at this stage. But the converse of this in particular statement doesn't hold. That is, we stated here, if H is a subgroup, then the order of H divides the order of G in the finite setting. Well, the converse of that would be if I have a divisor of the order of G, then I have a subgroup of that order. Well, it ain't true. The alternating group, we'll deal with alternating groups, I guess, in section 6. The alternating group I.4 is of order 12, and it doesn't have a subgroup of order 6. This you discussed in senior level algebra, I'm sure, as well. This is to be shown in exercise 1.6.8. If memory serves, it's not a very pretty thing to do. But here we have a group of order 12. 6 divides 12. It doesn't have a subgroup of order 6, though. So Lagrange's theorem says what it says. It doesn't say this. It doesn't say every divisor of the order of the group implies there's a subgroup of that divisor order. We might then ask, well, given a divisor D of the order of a finite group G, under what conditions does it have a subgroup of that order? And we'll look into that some in chapter 2 in the CeeLo theorems and in something called Cauchy's theorem. But let's go through proof of Lagrange's theorem. We're set to go on this because we have that previous result. All right. So we've got K as a subgroup of a group G, and we want to establish this cardinality claim. Take K to be the trivial group. Then if we look at the index of K and G, that's simply the cardinality of G. Trying to put this in the setting of the previous result. We had K as a subgroup of H as a subgroup of G in the previous theorem. So we're going for that setting. So take K to be exactly this, that produces for this index the cardinality of group G, the cardinality of K and H. Similarly, K is the trivial group, only has one element in it. That produces the cardinality of that intermediate group H itself. Theorem 1.4.5 says this index equals the product of those two indexes, or substituting in this index we had as a cardinality of G, this index we had as a cardinality of H, substitute in, and there's the claim. If H happens to be generated by a single element and we're dealing with finite groups, then this claim of division follows. You get this order divides that order, provided we've got the finiteness. And there's Lagrange's theorem. In itself, pretty easy to tell what's going on. This whole index thing is a little nebulous, possibly to you and me. You're counting cosets. Well, you're discussing the cardinal number of cosets, because that infinity stuff is just potentially everywhere. But we're looking at cosets. We're interested in cosets for some reason. At this stage, we're interested in cosets because they let us prove Lagrange's theorem. What we'll do in the next section, in section 1.5, is under certain conditions, we'll make groups out of the cosets themselves. They're called quotient groups, and I'm sure you saw that in senior level algebra. So let's call it a quits on 1.4 for now. We've got a few more things to prove, but I'll come back and do a finishing up video for the last few results in this section. Have a nice day. I will see you here again. There we go. Shortly, and we'll finish this up. We got through the bulk of this section. Catch you later.